So thank you for the invitation. And let's say, as we have seen, the key concept is in quantum theory is measurement. But let me start first with a photograph that already Federico showed in his presentation. So if you notice that the date of the presentation is 1927, and well, let's say not even 100 years from now. And what they were doing there was basically what we are doing here today now, no? Which is to talk about physics. No? So here, I think, to be honest, or let's say that's my personal opinion, maybe this is the most important photograph taken in the history of science. Well, that is up to the taste of everyone. But let's forget a little bit about quantum mechanics and go back to what we know. So as I said, the key concept is that of a measurement, no? And now let us consider that we are interested in measuring any quantity that we will call x, which takes a continuum of values, no? So for example, let us imagine that we're measuring the length of the table, let's say. So we take our spectrometer, we measure the quantity, and we write our result. Then we do the measurement again, and we write our result. And then we collect our basically measurement results. What the classical theory says is that the measurement result will be equal to the true value, whatever it is, plus something else. So that something else is called a Gaussian random variable. And in order to define or to try to define this Gaussian random variable, let us go back to some basic concepts of probability theory. So first of all, we should address that probability theory is basically the branch of mathematics which deals with random phenomena. And what do we understand by random phenomena? Are those situations in which one repeats the observation under a specific set of initial conditions, but one does not obtain the same outcome. No? So, for example, we are very familiar with the concept of probability in our everyday life. No, we say that it will probably rain this afternoon, or sometimes even, if I may make this comment, when I was reading the newspaper the other day, I read that unfortunately the Italian soccer team was out of the World Cup, not 2022. But then I thought, okay, so they will not play. But then it turns out that I read yesterday that the Iranian selection might be kicked out of the World Cup for some issues. So then this, in probabilistic terms, means that the probability of Italy playing the World Cup by not qualifying directly was non-zero, no? And I forgot about this detail, no? So let's see what happens at this. So as you see, also the notions of probability go back like centuries before. It was not until 1933 where the modern actions of probability were first written by Soviet scientist Andrei Dolgomorov. So among one of the key concepts is this of a Gaussian random variable. So in general, a random variable is a function that basically is such that its probability to take a specific value is equal to 0. And it turns out, let's say, it can be shown empirically and also theoretically that the measurement errors in physics are basically can be described approximately by a Gaussian distribution. So here I write down the probability density function for this Gaussian distribution. And this is a very old concept coming all the way back to 1733. So like many years ago, actually like 200 years ago, before the modern actions of probability theory were set. So with this information,
can I ask you something here? Gauss was not 19th century, right?
No, before, no. Before. Gauss, I think it was before. Yes. Yes, but let's say it's called Gaussian because Gauss was the one that let's say used it frequently in his calculations, but actually the Moss was the first one to introduce the notion of normal distribution.
Yeah, so the central limit came before.
Yes.
So my question was, how did the one call the function, the shape?
That is a very interesting idea, but I do not know. That is a very interesting idea. So with this concept, now, well, as I say, the title of the presentation was continuous measurement. No? So we need to introduce sometime a notion of continuous. So in order to do this, we need to complicate things a little bit, and we need to introduce now the concept of stochastic processes. So basically, stochastic processes are those basically random variables at each time. No? And one of the most famous stochastic processes is called the Wiener process, in which, well, here we are plotting just a sample path of this Wiener process, and you see that basically it's the case, and if we drew a sample path, we would have a different outcome. No? With this, now we can introduce the notion of a continuous measurement. So basically, we divide the time that our measurement takes into several intervals, no? And these intervals are of time delta t. So the continuous measurement will be obtained in the limit in which we reduce each time interval to basically 0, and the overall error is maintained fixed. So at the end, we have a measurement that is producing an outcome in each infinitesimal step. No? So we have, like, say, our true value plus basically this random quantity. No? And just a random quantity, the Wiener process is just characterized by a Gaussian distribution, basically, with variance tables. So now let us keep in mind this, in particular, this structure of the measurement, because we will come to it. So now let us talk a little bit about quantum. So let's say, reflecting a little bit, it all started on December 14th, 1900, when Max Planck, a German physicist, basically said that or introduced this hypothesis that the energy exchange between radiation and matter occurs only in integral multiples of a given quantity, which is the energy of a quantum. This quantity h bar, this symbol h bar appearing here, turns out to be a fundamental constant of nature. And given the fact that we are already talking about Planck, and given the times that we are living now, let me just briefly say an anecdote about him. So after the Second World War ended, the London Royal Society made an event to celebrate the 300th anniversary of the birth of Isaac Newton, the greatest physicist. And of course, it was after the end of the war, so they invited no German physicist except for one, and it was Max Planck. But when he was introduced at the conference, he was introduced as Max Planck from no country, because at that time Germany was divided by the, let's say, by the Allied powers, no? And then when the president of the society took the microphone, he said, let's say, I apologize for the presentation. It should have been Professor Max Planck from the world of science. So just to, let's say, to think about that science should transcend all the situations that we live every day, no? So this was in 1900, and then 25 years later, another physicist, another German physicist, by the way, Heisenberg, formulated his matrix mechanics, and then in the following year, Erwin Schrödinger here formulated his basically his wave mechanics. No, so these both were descriptions of that we still use now, basically to characterize quantum mechanics. Here, in this photograph, let's say we see them because at Stockholm train station, because they were there to collect the Nobel Prize, actually. And actually, it is quite interesting because, let's say, Schrödinger was older than Heisenberg and Dirac, so he was already married, so he invited his wife to come to the ceremony. But Dirac and Heisenberg were still very young. I mean, like Dirac was, I think, yeah, like not even 30, 31, no? So he invited, both of them invited their mothers to attend the ceremony, no? So just know, no? So in this Schrödinger equation that Daniel was discussing before, so they say all the information of the system is contained in the so-called wave function of the system, no? And the Hamiltonian basically encodes information about how to, let's say, drive that evolution of the wave function. No? So if we know the Hamiltonian, the thing that one has to do is to solve the equation, find the wave function, and with there, all the quantities of interest might be calculated. But it is unfortunately not that simple to do. So then now we come to the concept of continuous measurement. No? So you remember the expression that we had in the continuous limit of classical measurements, in which we had the true value plus the random variable. Well, in Gaussian continuous measurements, what we do is basically we are interested in measuring a quantity of interest, which now is called a quantum observable. And the true value, instead of the true value, we write down the expectation value of this quantity. So with this measurement record, one can find, let's say, in analogy of the Schrödinger equation, the dynamical evolution of the system due to the Hamiltonian and the continuous measurement of this observable. So we have that the final result is the standard Schrödinger evolution plus some term due to the continuous measurement, no? And of course, if already the solution of the Schrödinger equation was difficult enough, imagine with these extra terms, which depend also on the wave function through this expectation value. And this is called a nonlinear stochastic Schrödinger equation. So just to finish, why are we interested at this in particular? Why am I interested in continuous measurements? Well, so let us use this CGH scheme introduced by Matt Bronstein, by the way, and other Soviet physicists who unfortunately died very young in this great project. And by the way, just for the sake of general culture, another physicist very famous, which turns out to have been born on the same year and died on the same year, was Ettore Majorana, who made very important contributions in particle physics. But that's another story. So we are here in quantum mechanics, but as you see in this representation, we haven't introduced gravitational effects. So as soon as we introduce gravitational effects, things get more complicated. No? So one of the open problems in physics, or perhaps the greatest one of them, is how to reconcile quantum mechanics with gravity. So some proposals basically consider the description of Newtonian gravity through this continuous measurement idea. No? And let's say, maybe I in particular have been working on this concept. No? So just as a final slide, I think that there is like this, let's say, this interest in science that we all have also is in response to some challenges. I don't know if someone is familiar with this person. He was not a physicist, but he was born in what is now Ukraine, actually in Kharkiv, one of the cities which unfortunately has been subjected to this bombing, terrible. He was born in 1922, and in the 1950s, he was the discoverer of the decipherer of the Mayan script. So, 1945, a German linguist wrote an article saying that basically no one else, saying it was useless to keep trying to decipher this Mayan script because it was basically impossible. He said that he had spent 50 years of his life and basically has made no progress. No? So he was a PhD student, and his supervisor told him, well, maybe we should try to address this problem because I think that that guy is wrong, but we should prove that he's wrong in order to preserve the prestige of science. No? So they worked on that, and he basically gave the key ingredients to decipher this script, because he said, and I quote, "How come this problem does not have a solution? What has been created by a human mind must be understood by another human mind. From this point of view, there are no problems which have no solution. They may be known in any area of science." Thank you. Just by the way, sorry, I forgot. Unfortunately, his biography is only, well, let's say there was a book written by one of his students, his last student, Galina Ershova, but unfortunately, the biography is only in Russian and in Spanish. So, hopefully one day will be translated to at least to English. Well, okay.
Thank you very much, Jose. Questions, comments, observations?
If not, perhaps just to give a brief idea, I would like to discuss these models in particular, which implement gravity through this continuous measurement, just very briefly. I promise that I will take 2 minutes. Well, let's say we had these continuous measurements, no? And then one of the main applications of this continuous measurement is called feedback control. What's the idea of this? That you have basically a system, you measure it, you have an auxiliary system that somehow manipulates the measurement outcome. Then you do something else which you plug in the system to further drive the evolution to control it. No? So this is called basically feedback. No? One of the simplest protocols, let's say, was the 2 Washington and Milburn, and it's just basically to implement a Hamiltonian which is directly proportional to the measurement record that we wrote before. So then you have basically you are to a master equation which involves the continuous measurement of the quantity of interest plus the evolution due to the feedback and some interaction term. No? So with this term, which basically resembles a standard Schrodinger evolution, some years later, in 2014, Capricello Taylor and Milburn recovered a linearized gravitational interaction. How did they do that? So they consider a couple of particles which are basically oscillating and which are interacting among themselves only through gravity. No? So if you linearize the gravitational Hamiltonian resistance, you arrive at this expression. And then the proposal of Capricello and Milburn was to replace this Hamiltonian in such a way, let's say, in such a way that the evolution of particle 2 is influenced by the measurement record of particle 1 and vice versa. One can show that at the level of the master equation, one recovers the standard gravitational interaction, but the price to pay is basically the appearance of some decongruence effects. No? The advantage of this kind of models, although they are simple, is that they are experimentally testable. No? So that represents, I mean, at the end, they can shed light of basically determining the quantum or not quantum nature of gravity. Okay, thank you.
Thank you. Other questions or comments? I have one question. The modification of the Schrodinger equation that you showed us at a certain point. Yes, this one. How does it differ in the logic, if there is any difference, of course, from what one does in classical mechanics by writing the Giovani equation, or the Fokker-Planck? So also there you have the Poissonian brackets, which gives the usual Hamiltonian evolution, and then you have a noise term, which is of inner type, which gives rise to diffusion. So is this just this one that you are showing on the screen? Is this a sort of quantization of this procedure, or is there some differences? Are there some differences between the two approaches? I mean, yeah, between this one and the other one. So I mean, the Brownian motion is something that could you term that quantum Brownian motion, or are there differences?
No, I think this is just okay. The Brownian motion remains classical, no, in this approach.
Yeah, sure.
To be honest, I'm not that familiar how to derive the Lagrange equation, but in this, I can tell how to derive this equation broadly speaking. So basically, from this measurement record, what one does is to construct basically Gaussian weighted operators, no? which basically encode the measurement record. No? And with these Gaussian weighted operators, one checks that indeed the probability of obtaining the outcome, let's say X, is given by the expectation value, so they coincide. And with this, one basically just applies this operator to the system at a time t plus delta t, and then just one expands the cycles and arrives to this this classification equation.
or I rephrase my question rather. If you do the classical limit of this thing here, do you get the Giovani equation or the Fokker-Planck equation?
I don't think so, but I don't know. But I should check, to be honest.
I think something more similar to that, the Lambda equation would be to add some standard stochastic potential with some dW without all the nonlinearities.
Okay. In fact, I was suspecting that the nonlinearities there are what makes this process different from a simple quantization of the Brownian motion. Okay. Thanks a lot, Jose.